Good afternoon, everybody. Thank you very much for being here. I'm Jeremy Pico-Clement, technology expert at EPIC, and I'm really pleased to welcome you for this online technology meeting on photonics for new display technologies. Before to start, I would like just to introduce EPIC to you if you are not aware of what is EPIC. EPIC is the largest industrial network in the world in the field of photonics. We have today more than 800 members, covering all the value chain of the photonics industry, from the component manufacturers, the design and prototyping company, to the end user and system integrators as well. We also cover all the photonics applications, so imaging system, defense, space, biomedical, quantum, but also AR, VR, agriculture, PICs and laser technology. Everything, everywhere where you can find some photonics technologies, actually. So our aim is to create a sustainable European photonics industry. And how we do this? So we offer to our members a large panel of services from technology support, market and technology reports, networking event and opportunities, access to market if you want to develop your business in the US, North America, or even in Asia. We are able to support you. Also mentorship, HR support with the website Jobs in Photonics, and also investment support. We have a list of investing companies which can be involved with you depending of your needs. Here is a team, the EPIC team. So we are all passionate by photonics. We have a marketing team, a logistic team. I'm personally a part of the technology team in charge of optics and optical system. And I have two other colleagues in the technology team, Antonio Castello in charge of biomedical and lasers, Ivan Nikitsky, expert for quantum and integrated photonics. Few words about the next event we will organize. So about physical meetings, of course, we will be at Photonic West. We'll have a booth there, so feel free if you are here to come to our booth and take a coffee with us. We'll be also at APE in Singapore. We will organize in March an interesting technology meeting, physical meeting on photonics integrated circuits at Lagentech in Switzerland. We'll be also at the W3 fair in Wetzlar, Germany, and we'll organize Tech Watch there. So if you are there, you can also participate and talk during this Tech Watch. Please feel free to come to us, to contact us for this. And end of March, we'll organize the annual general meeting in Barcelona, in Spain. And we'll be also at OFC in San Francisco, 1st of April. Regarding online meetings, so every month we're gonna have several online meetings. So in December, we'll have something on new product release for our members. We'll also organize an EPIC HR work group, transition of new executive management. This is the topics of this work group. In January, we'll have an online technology meeting on photonics for quantum industry. 14th of January, we'll have a market report on semiconductor laser industry by YOL Group. And the 21st of January, something that could interest you, we'll have an EPIC market report on premium display technologies by Jan Handy. As I told you, we cover all the photonics industry, all the value chain, and here are the companies that registered for this event. So we have some company from the component and module sides, consultancy, equipment manufacturer, end user and integrators, mainly from the AR/VR actually here. R&D also, service providers, software and design, metrology and testing, materials, contract manufacturer, foundry. So yeah, we cover all the value chain, and you will have access to this slide after the event, of course. And here is the agenda of today's event. We'll start with Sebastian Rettinger from Alpha Mission. He will talk about pixel shooter text equipment, test and text. And then we'll have a presentation by Uwe Vogel from Fraunhofer IPMS. He will talk about semi-transparent OLED micro displays for future wearable optical systems with AR. We'll continue with Jan Gouling from the Cube Dot company. You will present the Smile micro-LED platforms as a customer-centric display solution. Then Oliver Haupt from Coherent, enabling industrial micro LED display manufacturing by DUV laser solutions, a future-proof approach. We'll continue with Søren Stødel from Mikledi micro display. You will present yield and manufacturing challenges for micro LED micro displays. And we will end this meeting with Peter Karp from Admesi. You will have a talk on measurement of new display technology. So thank you very much for your attention. If you need to be introduced to some of the speakers or the participants of the today's event, feel free to contact me. I would be pleased to do this for you. If you have any question, you can send me an email. And also something that is really important is that take the opportunity to ask questions and to discuss during this meeting. It's on 2 hours, and after each presentation of our speakers, you will have the time to ask your question. So thank you, and maybe now we can start with the first speaker. So Sébastien, you can share your screen and start your presentation if you're ready.
Okay. All right. Thank you, Jeremy. I think you should be seeing my screen now.
Perfect.
So thank you for the opportunity to talk today. I think some of you already heard me talking last week in Amsterdam. And I'm going to talk today for Alphamation about display functional testing. So when it comes to making sure that the products, the end product, or even some components meet the requirements once they are produced on the production line. So just a quick word about myself. I am in optics for more than 12 years, and 10 of which for Alphamation, where we build automated test equipments. So just about affirmations, since March this year, we are part of the InTest group. It's a US-based company with the headquarters in New Jersey. And there are 3 different divisions. Electronic test division, where Alphamation is sitting. Then we also have environmental division with thermal solutions, and also the process division, providing also a solution for semiconductor process technologies. Alphamation, the headquarters is in Italy, in the northern part of Italy, and we have about 130 employees. The strong characteristic of Alphamation is the very strong engineering team and the capability to adapt to the innovation of the different industries where we work, like consumer electronics, automotive systems, including displays, infotainment systems, and also micro-optics and photonics. A quick overview of the systems that we build with different shapes, different sizes. Some of them for electronic testing. We also make some modules, individual modules that we sell as a standalone instrument. We use them also inside our equipments, and we have some functions like video generation, communication protocol, and we use them to communicate with the displays, for example, sending signals, video signals or comments for the display. We do have also a wafer level test platform, which I talked about last week, but today I'm going to focus on the pixel shooter platform, which is the one you see here that we use to test display. And as I said before, the challenge that we have is to ensure the quality of the display in the production line. And to do this, we verify different functions of the display, like electrical and firmware functions. So basically verifying the voltage, currents, consumption, and so on. We also have inside the system optical verifications, like defective pixel, color measurements, brightness, contrast, uniformity, flicker, and so on. And when the display has also a touch function, for example, we also have haptic testing solutions with fingers, robotized finger, for example, or vibration sensing, to make sure that also the haptic feedbacks are working. All of this we do in one single test station. So this test station that you see here can be fitting all the tests that I described just now. And I'm going now to go in more details on what kind of implementation we do and how we do this inside. So a typical system is made by a vision camera, high resolution, about 50 megapixel, sometimes 30 megapixel, depends on the resolution of the display, which is to test. We have a SCARA robot, which has here the possibility to load different end effectors, different tools like fingers for touch, colorimeter to test flicker and colors, and also we have fingers with multiple fingers to test multi-touch functions with 5 points or even more. And we have different kind of interfaces with the line, with the operator. It can be manually loaded or also interfaced with an external robot, loading automatically the device under test inside the bay. And this tester that you see here has a rotating table. And this rotating table has the advantage of having two devices loaded at a time. One on the outside, which can be loaded and unloaded. And we can already start to boot it up and do some tests, electrical test. And the second one is inside the tester, doing optical tests and touch tests with the robot. Once finished, the table rotates, and you can, in this way, optimize the cycle time. And this is an example of a real-life test cycle that we did on a display. And with all these steps that you see here, including electrical test, some firmware programmation, touch test, color test, ambient light sensor test, and so on in 58 seconds. And you see here in gray on the bottom is the same test going on the second display on the rotating table. So you can see the benefit in terms of parallelization of the process and the gain in time. This is a quick overview of the setup we use to calibrate the ambient light sensor on the display, if it has it. We do use a white LED light source with a collimator to shine directly on the light sensor on the display. And this illumination is calibrated with a lux meter to make sure that we calibrate the sensor to the lux reading from the calibration. This is an example of pixel defects detection. This is a simulation of a display of a defect by putting an image simulating a black pixel, and with an in-house algorithm, we can detect down to the sub-pixel defect. We also developed some uniformity and Mura algorithm looking at some bright and dark areas on the display, and we use the standard which are defined by the German automotive standard in terms of algorithm to find the defects and being able to put the limits according to the standard. And this is an example of the Mura test with the gradient image. So the Mura test is basically looking at gradient variation into the display, and typically with this test you can see if there is stress on the display which is put and giving some bright areas. So just to finish, and this is the usual question, that what we are looking for is to keep pace with the evolution of the technology. Right now I talked about displays about 10-12 inches for automotive, typically, like instrument cluster, infotainment system displays. And we are looking at also testing different kind of displays like micro LED, OLEDs, also head-up displays, and potentially also holographic displays. It's for sure quite a challenge because maybe most likely the way of looking at display is different than what we do today. And this is what you can do for us, maybe having a test case that we can work together on to automate it, or if you have an instrument that does a test but needs to be integrated in a platform, we can also do it. As I said, we have a very innovative mindset in Alphamation. It's been 33 years of innovation so far, and with a very strong engineering. And we do have proven platforms that we developed over the year that gives quite some comfort in this development because we have a good base to work on. So that was it for me. Do not hesitate to get in touch later or ask questions right now. Thank you very much for your attention.
Thank you, Sébastien. Thank you very much. Any question for Sébastien? You can raise your hand through Zoom. You have a button at the bottom. I have a question, Sébastien, for you.
Yeah.
What is the most the most common defect detected, in micro display during your testing process? What is the most common defect?
In micro display in particular, you mean? Or in
general? No, mainly in micro.
Because micro display, we don't test them as per today. It's mainly bigger displays for automotive. And the main defect we are looking at are defective pixels. Lately also there is a strong request for color calibration, white point calibration. Which is getting like some kind of new request. In the past it was not so tight requirement on this.
Okay, thank you. Question? Okay, so if we have no more questions, thank you again, Sébastien, for this nice
Thank you.
presentation. So let's move on now with our next speaker. So welcome Yue Vogel. Yue, you are head of business unit micro display and sensors at Fraunhofer IPMS. So Yue, you can share your screen and start your presentation.
So thank you very much, as well as for the kind invitation for today's talk. So I assume you can see my screen well. Thank you. Okay, so I will focus today on semi-transparent CMOS backplanes for advanced near-to-eye micro displays, which will be mostly used in optical see-through augmented reality. My group has recently moved from Fraunhofer FEP, so another Fraunhofer institute, into Fraunhofer IPMS, and IPMS stands for Institute for Photonic Microsystems, and I think such sort of micro display is indeed a nice example of a photonic microsystem. I mean, just to give you an idea, we are based in Dresden, Germany, or the southeast of East Germany, and specifically the ecosystem here in our area is very important also for the sort of work that we are doing. So let's say we are very closely related to microelectronics, and we are also collaborating with those fabs that are really in walking distance from our site. So here is the Dresden airport. We are situated here. And there are the fabs of Global Foundries, Bosch, Infineon, X-Fab, and some others really close. And that is really a kind of prerequisite for what we are doing here. With respect to microdisplay technology itself, you might more or less briefly distinguish between emissive ones, which are mostly today non-transparent, as well as some other technologies like reflective, transmissive, and scanning devices. I will focus today on the emissive ones, and there are two major emissive microdisplay technologies, OLED on silicon, and the next speaker, Jan Gülling from CubeDot, might also focus a bit more on micro LED later on. So, and the major difference between those emissive and all the other technologies is that the light source and the image modulator is the same, and that actually provides the best and form factor for such devices, since you don't need an external light source as a separate device. And as I already mentioned, mostly the backplane, so it's typically a CMOS chip, are non-transparent. And now the idea is to make those transparent to make for optical see-through devices even better form factor approach than we have today. So what are the common challenges for optical see-through devices? So to optimize field of view, very high resolution, PPI and PPD, brightness, color weight, form factor, iBox, focus Q, mutual occlusion, and of course manufacturing cost, and all of them simultaneously. And there are a few types of different optical see-through approaches so far. So for instance, a 45 degrees flat combiner or bird bath optic, which is rather simple, but also comes with a few issues like form factor versus field of view efficiency and also optical distortion. There are also freeform approaches that are very compact, but also come with optical issues, for instance, with respect to Rochon's accommodation conflict. And rather popular today are waveguides, so specifically also diffractive ones. They provide a rather good trade-off in form factor, iBox, and cost. But, and that is really an important issue, specifically in wearable applications where you always have a very limited battery capacity, is their low efficiency, their low optics efficiency. So, and often a narrow emission from the light source is required. And narrow is in terms of angular emission as well as also spectral width emission. There are also a few other approaches. Okay, but these waveguides typically require very high luminance light sources due to these low optical efficiencies, and therefore mostly LCOS, liquid crystalline silicon, also MEMS-based spatial light modulators, as well as micro LED are being considered necessary as the light or image source in such waveguide devices. But the drawback is the very high power consumption that is required. For instance, Gertech has shown a monochrome micro LED based projector device for near to eye consuming 1 watt monochrome, and for RGB even 2.5 or 2.4 watts. And this is just too much power consumption for wearables. And why? Because the battery capacity in a wearable should not be more than 1 watt hour and should still enable 12 hours of continuous operation. And that actually means that the entire electronics, including not just the display, but also sensors and microprocessor, microcontroller, and so on, should consume less than 20 milliwatts. And the light engine itself, only 5 milliwatts or even less. And that is not achievable with all the other devices. But the issue is, since OLED can typically not, or let's say, cannot reach the brightness level that is required for waveguides due to the rather wide emission spectrum and the too low luminous flux, OLEDs are typically excluded for such engines, display engines with waveguides. So, and there's a solution to come along with semi-transparent emissive micro displays or micro display backplanes. And one effect will be that the display itself becomes a combiner. So nowadays we have such sort of setup, a non-transparent display. We have these combiner optics with exit pupil expander, and now we move over to a semi-transparent micro display backplane, so you can directly look through the micro display, and you still have some additional optics in front to provide the virtual image. So that would be the new approach. Then that means we don't have optical or significant optical losses anymore, and we can really live with a moderate light engine luminous flux in the setup. That means OLED will become sufficient again, and OLED on silicon is already a mature technology. Micro LED will still be valid and appreciated for that approach, but micro LED, at least in my opinion, maybe Jan will look at it differently, still has to become mature to some extent. So, and there are two general optical setups. We call it sparse pixel versus cluster approach. So the general idea is to really leave transparent circuit layout spaces in between either pixels or clusters. So that's a cross section of a general emissive micro display. So here in that case, we have seen typically non-transparent silicon backplane, and we have the organic or OLED front plane. And as I mentioned here in the statement, we leave some space in between individual pixels or in between groups of pixels, and this space in the backplane will be transparent or semi-transparent, and then we will also get an overall semi-transparency. And this is achieved by making use of SOI, so silicon on insulator, CMOS backplane wafers, so they actually feature a thin active SOI layer on embedded or on top of a silicon dioxide. And in so-called bulk silicon, this active layer would be in a non-transparent silicon layer itself. And now we have, as a so-called handling wafer, we have another silicon substrate underneath. So what we now do is that we perform the processing based on our design of the SOI wafers at a silicon foundry, then receive their wafers back. We continue with the emissive or OLED layer or front plane stack on top of that, and then we actually remove the silicon handling wafer, and then we have this transparent spaces in between the individual pixels or clusters, as I have shown before. So this gives you an idea. So here, this is a backplane including several micro display devices on the SOI wafer. It's not yet transparent there. Then we perform the OLED front plane integration, and then we apply this transparency process, so the handling wafer removal, and then the devices become transparent or semi-transparent. And this is what we currently have. So such sort of device. It is how to say, designed in clusters. So we have 7x4 clusters, and each of the individual clusters has 256 by 256 pixels. It can also be used in an RGB arrangement. Then you have half the resolution, and the individual clusters are roughly 0.9 millimeter by 0.9 millimeter in size. The individual sub-pixel size in such a cluster is 3.5 micrometer. And the cluster pitch is 2.2 millimeters. So the 7x4 clusters at 2.2 millimeter pitch. And that means we actually now put here, you can get the idea of the 7x4 cluster. And now we put a micro lens array it's the same size, so 7x4 micro lenses on top of this emissive semi-transparent backplane. And in our first approach, we have actually achieved 22% of optical transparency. We have shown this last year already, and this year we have been able to improve that to 45%. And that is some sort of image taken through the optics, so of course including the micro lens array and through the semi-transparent backplane. So let me conclude with some outlook. Of course, high brightness is still a topic. Although the luminance that for optical see-through that is required by the semi-transparent backplane approach can be much, much lower. So typically 5,000 nits or so will be completely sufficient. And high resolution is obviously a topic. I already mentioned the 3.5 micron dot pitch in the semi-transparent device. But we have also shown the 2.5 micron dot pitch on a non-transparent backplane, but on a 300 millimeter, 28 nanometer CMOS backplane node. Embedded sensing, embedded connectivity. Of course, also micro LED might be an interesting topic also for the semi-transparent approach, but for instance, also for extended spectral emission and detection ranges, and obviously new form factors. So transparent, I already discussed, for instance, also for use in future smart contact lens applications, but also such sort of curved devices that can really enable again increase or improve form factor of such optical devices. And that's it. And still, let's say the obvious AP questions. So what can IPMS do for you? So of course we can perform such customer-specific micro display design and also pilot manufacturing. We are working with silicon foundries on both 200 and 300 millimeters and make the OLED front plane in-house. and of course we can provide such sort of backplane transparency process. And we are looking for partners, for instance, for collaboration with wafer level micro optics designers and suppliers, as well as with system integrators. And that's it. Thank you for paying attention to my presentation.
Thank you very much, Huey, for your nice presentation. Any question? What is the level of maturity of your semi-transparent display? How far are you from the industry?
Yeah, that's a good question. I mean, we are still in the beginning. I mean, we are able to show working demos, working prototypes. I had mentioned just last week I was at IDW, International Display Workshops in Japan, and there was quite some interest about the technology, but it's still, how to say, development required. So, I mean, also with respect to the optics, and as I also mentioned here on this last slide, so we are not really optics experts. We are in the photonics. And let's say specifically also the wafer level micro optics that will be required for efficient manufacturing. That is nothing that we think we have let's say, the processing and integration capabilities for wafer level optics, but we cannot make wafer level optics ourselves. So that is something, for instance, we are interested in. And so this will still take a few years, I think, to get into products.
Okay, thank you. We have a question from Jan Gouling from CubeDot. Please, Jan.
Yeah, hi, Uwe. Thank you for the nice talk. One question on one of your slides, I think you stated that the overall light engine should not consume more than 5 milliwatts. And as I'm a micro LED guy for the future, you're rather looking then for high efficiency of the micro LEDs, and you're not aiming at the super highest brightness. I mean, you know that you can put a lot of current into them, but in your opinion, it doesn't make sense from the system integration point of view. Is this correct?
Yeah, that's correct. I mean, something that we indeed envision by using micro LED in the context of those semi-transparent backplanes is not really about the brightness, and also probably not about the power efficiency. I mean, I would I would laugh if you can show me devices, let's say at maybe 1 micron dot pitch, that have a better power efficiency than OLED. But since we do not really need a very high brightness in this setup, it might help, how to say, to even improve the transparency by being able to make the let's say, the micro LED at a comparable luminance, smaller than the OLED pixels, maybe. But I mean, of course, still you need, let's say, the driving electronics, and I mean, you know yourself. I mean, we might need a somewhat higher, let's say, current density. That might even make the driving transistors larger than those that we need for the OLED. So that is something we still have to explore, and maybe together.
Thank you so much.
Thank you, Jan, for your question. Maybe something else regarding the smart contact lens application you mentioned on your last slide. Do you have any related projects you are part of?
Towards the smart contact lens itself, not yet. But I mean, the motivation for developing such sort of, as we call it, transparent microelectronics and curved microelectronics. So you actually need both for the smart contact lens application. So that is, how to say, our longer term vision, but for the same approach.
Okay, thank you. And if we have no other question, I would like to thank you again, Uwe, for your nice presentation. Thank you.
You're welcome. Thank you.
And now let's move on with our next speaker, Jan Gouling. So Jan, you are co-founder and CTO at CubeDot. So please, Jan, you can share your screen and start your presentation.
Yes, I hope you can see the shared screen now. If this is the case, let's start. So my name is Jan Wülling, and today I want to present to you the Smile micro-LED platforms as customer-centric display solutions. And in the beginning, let me firstly introduce shortly CubeDot. We were founded in 2019 based on 45 personal years of development with a unique technology to process the gallium nitride material system. And we're a passionate team of around 15 employees at the moment. And the difference from our view to the big players is that big players, they do not touch their standard processes, and we do offer customized and standardized products in this case. And we're safe to provide designs from 1 micron to 1000 micron. So it's not only micro LEDs itself. Let's have a look at very first Smile platforms with the monolithic approach. These products are kind of the first step into the door products. We offer 6x16 micro LED arrays with a standardized contact ring and different pixel sizes of the emitting array. These platforms have a frame rate, a real frame rate of 170 kilohertz. And most of the time they give a very first impression of what micro LED technology can actually do. And then there are other systems with, for example, 8x8 pixels that can be modulated pretty fast. In this case here, and 5 micron pixel, 5 micron gap, so 10 micron pitch, 8x8 array modulated with 1 kilohertz from pixel to pixel to pixel. The gallium nitride material system, of course, works best in the UV to green range. But nowadays, we have also tweaked our epitaxy in a way that we can offer a decent red emission, of course, at lower efficiencies, and a small shift from red to like orange that's possible via the current density. As you can see here also on the images, these red micro LEDs have feature sizes down to 3 micron, and you can see a lot of different shapes and forms that are possible. The wavelength is tunable and it can be adapted to customer designs. I want to stress again that how we process micro LEDs itself, that the pixel form is rather size independent. And for this, I want to show some impressions on this slide. So the pixel doesn't have to be round or square, like you can see on the left side of the images. A pixel on our side, it can also be a complete sign or the letter itself. For example, on the bottom right, you can see this, that the CubeDot logo itself is just like 1 pixel that can be, for example, useful for information displays. Our technology also allows us to produce quite some interesting aspect ratios. So on the top right, you see a micro LED line array where each line is 7 micrometer thin, but 5,000 micrometer long. So that is also for some use cases very interesting. And like I shortly said, an example might be information displays, where in the off axis you want to provide information at a scale where you already know, okay, there will be a battery sign or there will be a lightning sign. You do not need to have a completely integrated micro LED display over there. You can just have an information display where the pixel is the sign you want to showcase anyway. I want to move now a little bit big to general assembled displays. On this slide, once we agree with Joel, if you want to make micro LEDs successful, you have to reach high efficiencies at the single-digit diameter regime in micrometers, and you need a transfer with a very high yield to make the step from prototype to product. And I'm pretty sure that after my presentation, Oliver Haupt will talk a little bit about it. So, as I said, we at CubeDot produce micro LEDs, and we bump them, and we bump the backplane, and we do the transfer with the tools available from our transfer toolbox. And as you know, all the calculations, even if you have a transfer yield of 99.99% on a 4K display, that still means that you have 2,500 dead pixels, and that's not acceptable on a customer level. So good micro LEDs on wafer level are nothing without a proper transfer and the correct interconnection technology. And that's why we as well perform laser lift-off after bonding or laser-induced forward transfer for the direct micro LED transfer and bond. One other important point that I really want to stress today is that at the moment, there's no golden way in the micro LED industry. Every company and at every stage works on their kind of own micro LEDs and try to come to the solution. And we also offer this customized solution. And for different use cases, the customer also might some different brightnesses and emitter solutions. That's clear. However, standards regarding die size, contact sizes, and emitters have huge benefits at the interfaces of all the industry partners. And these standards are not there yet. At least I do not see them. So we at CubeDot, we do offer our customized micro LED solutions, but we do also offer standardized solutions. And like, for example, here on the bottom part of the page, you can see die sizes of 80 times 80 microns, so like rather mini LEDs with different contact pad configurations that are ready to transfer. How does this look now a little bit more in detail? For example, if we assume dies with 14 times 14 micron, like on the left side, we can produce wafers with these micro LED dies, and we can pre-bump them on the wafer. And I think from this type of die, like on a 6-inch wafer, there should be like around 150 million LED dies, roughly around this. I think more interesting is on the right side, the zoom in on the SEM image, where you can actually see that like contact forming is possible here with these triangle shapes. And this is something that we offer. Nowadays, they're always customer specific. And I said that like LED solutions without a transfer are nothing. And just to showcase this, we do transfer them successfully, in my opinion. These are the same dies that we have seen on this slide before. So on the left side, you can see several cross sections from the focused ion beam, showcasing that we have rather defect-free interconnects at this part. And on the right side, you can see the small gap after the transfer that most part of your display, if you would bump your display with this type of die, that the fill factor is high. Of course, for example, in the case of UV, beforehand, when you want to do a transparent micro LED display, you would just choose a higher gap between the LEDs after transfer. That's feasible on this part. So we at CubeDot, we deliver your micro LED mostly again on Sapphire solution. We do this on our customized, on a customized basis, but we also do this on standardized die geometries that are directly and faster available. And the limits of this process, of the standardization process, are given here relative to the die size on this slide. And I also want to express again that after we have identified together with our customer and the interested parties the correct die size and emitter size and contact configuration, we do perform partly also the transfer with our transfer toolbox. And that's mainly it. Thank you for listening. And if you want to contact me, here are the information.
Thank you, Jan. Thank you very much. Any question for Jan, please? Raise your hand. Jan, what are the key markets segments you are targeting with your customizable, technology?
Yeah. So the most important market for us is actually light engine development for augmented reality of companies that cannot be named yet and is like under NDAs. We do also produce micro LEDs for metrology, especially when you have very defined point sources, and for microscopy, for example, and for sensors. But also main driver for us is the display market.
Okay. And is this process longer than a normal process, and if yes, how much is it longer?
Sorry, can you repeat that question again? I did not fully grasp it.
Is your process you are developing is longer than a usual process, you know?
In comparison to what process? Of course, we have not so many mask layers, so we're always faster than the CMOS industry, and we can adapt more quickly our light sources, for example, to CMOS backplanes, where feedback loops are way longer. That's definitely a plus on the versatility side. And of course, we can produce wafers and use them on several different backplanes, especially if we reach a higher degree of standardization. I hope this covered the question.
Yeah, thank you, Jan. Any question? Okay, so thank you again, Jan. And just for you to know that we'll organize an epic meeting at Photonics next year in June. And it will cover all the augmented reality topics. So, and we will have a session really dedicated to display and you know, display technology. So it could interest you.
Perfect. Sounds like a good fit. Thank you.
Exactly. So thank you, Jan, again for your nice presentation. And now we welcome Oliver Opt. Oliver, you are Director of Strategic Marketing for Display Capital Equipment at Coherent. So Oliver, if you are here, you can start sharing your screen and start your presentation.
Of course, I'm here. Thank you. Yeah, I think there, for you, the French guy, the names are not so easy, right? Can you see my screen now?
Perfect. You can start.
Yeah. So yeah, welcome. Yeah, perfect order of presentations now. So Jan explained a lot about the micro LEDs, and I will follow up with some post presses now and show how we enable hopefully the micro LED display manufacturing. I'm mainly focusing on our deep UV laser solutions. I have one different example, and yeah, we call it always now our technology is a future-proof approach, and I will show you why. So. So we are the equipment manufacturer for display or all kind of displays, and from this perspective, we are looking to the market, and we see the micro LEDs now, yeah, starting in small application like we discussed AR. I think it's the best light engine solution today. But we are more focusing on larger areas because, yeah, the larger square or the more square meters we have to, or our customers have to produce, the more equipment we can sell. But we learned over the last years now that yeah, who is your stakeholders or key players in this market, and I'm always explaining now that, like you have seen, we need a good EPI. So we need a good compound semi micro LED. They have to get small. They have to get high brightness. But so if we go to larger formats, we need also display makers, and that means also we need display equipment. And this is our play where we are yeah, familiar with, and we are known in the market for laser equipment, in mainly, of course, in OLED now, but we have already a very good footprint at this early stage in micro LED display, let's say pilot lines and manufacturing. And yeah, it's important when you talk to the big ones that you can offer a 24/7 service and machines that run yeah, even 24/7. So that said, our main focus is on a little bit on larger formats, because yeah, this is the main market where we think we can sell our laser based equipment. And of course, what we see is that the new technology, like also the OLED technology now or in the past, there are a couple of laser processes that are mandatory or at least helping to make a good display. So here is my overview and the process chain, and I think the different to OLED is that we have different fabs. So the EPI could be completely separated from like the display fab, where we make the final displays, or the display makers make their final displays. They can purchase or buy an EPI wafer or already a processed wafer, what we call the laser lift off. So getting the micro LEDs pre-qualified on a temporary carrier. And the third part is also that what we see for larger formats is the backplane technology. So when you walk through shows and see everything like automotive size displays, almost all are made on LTPS backplane, and this is also our main core market. So below you see the 4 different core processes where we are playing with our lasers today. It's the lift off, to release the micro LED from the EPI wafer, and then the mask transfer. And yeah, sometimes you need a repair, so we want to address a single micro LED to remove it or refill it. And nowadays, this 4th process is not a UV process, but laser assisted bonding. So after the transfer and after the repair, the final bonding step can also be done by a diode laser at a different wavelength. So I will have a short example. So what I said, backplanes are our daily business. So we have more than a decade or more decades of mass production, and it's always what we call the de facto is a standard for all OLED displays today. And as I said, if you go to shows, you will see for TV or TVs or automotive or larger micro LED displays, you will also see the LTPS. So next generation backplanes can be used almost like the OLED displays. And we also see that we have to, or the new fabs are going to larger formats, not now to generation 8.6 to keep the economy of scale when you go to larger displays. And yeah, what we see is that almost every display maker in the world has already access to the LTPS backplane. So they can use more or less their standard equipment, and with little modification, they can make backplanes for micro LEDs as well. So this is the first step going to LLO, and also we are focusing mainly on gallium nitride on sapphire, like Jan said also. And this is a very traditional process now, the lift off. Due to material combination and due to the fact that we want to absorb in the first nanometers of the gallium nitride buffer layer, the short UV wavelengths is mandatory to get a damage-free laser lift off or between the gallium nitride layers and the sapphire wafers. And yeah, so we started many years ago, and what you see here on the right hand side today, looking a little bit on the productivity, you see with that, of course, there are, let's say, solutions available where you use a small single spot to do the entire wafer lift off. So here we are focusing or targeting more the less than an hour per wafer. Then we offer a little bit faster processing, so like small square spots with our laser systems, where we talk about minutes. And then the fastest solution, we can also go up to a line beam system to cover a full 6 or 8 inch wafer and process this in a few seconds. So all this is mandatory with very deep UV wavelengths. So in this case, we are using our 248 nanometer lasers. Yeah, as said, the most challenging is the transfer. And there are many different, so as Jan said, no golden standard. So we are working on this, but you see that we with all the customers we are working today, they have different ways how to make a micro LED display, how to make the transfer. And there are ways to, or customers are interested to go directly from the epi wafer, transferring the micro LEDs selective to a backplane. Some are getting already micro LEDs on a temporary carrier and shooting them to a backplane, or just preparing the what we call a second donor. So making the RGB on a donor template, and then it can be done by mechanical bonding to make an RGB displays. So there are many ways. We see all of them in the industry already, and yeah, so we also try to help customers to find a golden standard like we see in OLED today. The good news is we have solutions to offer all the different approaches, and our equipment is capable. That's again why we say future proof. Here you see we learn from 5x5 micron. This is a target, and also Jan mentioned this already. So this is we are looking. The larger micro LEDs are easy to transfer for us, but we know that they have to get smaller. The material has to, material cost has to come down to make the micro LED displays cost comparable. And the question is, will it ever happen? So are we getting the efficiency, the EQE of the small micro LEDs to make them industrial available? And we are looking onto 5x5 micron now to see how our solution can transfer these 5x5 microns. And as you see here, they are already perfectly transferred. So again, future proof. The laser mass transfer we are using in our setup goes beyond the current limits and can handle already 5x5 microns. Yeah, that's it. So the backplane, now we have done the laser liftoff and mass transfer, and a little outlook what is next. So after, we hope that we don't need too much repair, and now more and more interest we see in laser assisted bonding. So after the final transfer, the micro LEDs are sticky or sticked on the backplane on bumps, but not really bonded. And here there is a process called laser assisted bonding. So this is a thermal process. We are using a 980 nanometer wavelength diode laser. Also, we can create, as you see on the lower left, lines or square beams, and with this we can very precise heat up or the micro LEDs and do the final bonding process to the backplane. The laser assisted bonding also is not new. It's used already in microelectronics. So it's let's say an industrial process, but now we are adapting this to micro LEDs, and yeah, that's where we see a lot of interest now after the transfer is already solved. Again, our customers have the choice. So we are usually an OEM supplier. We offer lasers, deep UV lasers in different power classes. We are having a big team designing different kind of optics. And for the micro LED, we decided to go one step further. And because of the complexity of the transfer, we are working to, or we have a tool available to make all the good results and the precise handling. So this is what we offer to our customers: repair, mass transfer, laser liftoff. Laser assisted bonding is the fourth new process. And yeah, that's it. So my summary, again, you need a good compound semi company to make a good micro LED micro LED, then you need a display maker and also some display equipment to make a good micro LED display. Yeah, they must get small. Lasers are known for precise processing. That's why we are in the market, and that's why we are looking into this in more detail. And the second is that we have seen that lasers are essential to do the micro LED or making micro LED manufacturing available. It's a future-proof process, and we know how to scale. We have done this for the OLED industry, started at the small generation displays, and today we are scaled up to large Gen 8 panels for OLED. So we can grow with the customer needs in the display fabs. That's what we see. The question is, will it get real? At least we are on a pretty good path, and we are ready. Let's say we're just waiting that others follow us. Thank you.
Thank you very much, Oliver, for this last presentation. Any question for Oliver? You can raise your hand through Zoom. So it's quite clear what you can offer to the industry, Oliver. But what could the industry offer to you? What could the participant of today's event could bring to you?
Yeah, so the one is that we see that you need more and more, let's say, in one hand. So we look into, let's say, into bonding materials, because they have to get also smaller grain sizes. We are looking into what kind of temporary carriers can be used, and even we want to understand what is the way to success for the EP companies to get to higher AQE on small micro LEDs.
Thank you. Any question? Do you have any development, any laser technology development to address, the ultra fine pitch display today under 5 micrometer, for example?
So our technology, usually what we're using, we claimed in the past that the resolution is 2 micron, but you need a little so from optical perspective. But if you talk about a tool, you have to do to take also the mechanical tolerances into account. And while we are focusing on larger displays, we focusing on displays where you need the pitch conversion, and there you usually don't need a single addressing of a 2 micron micro LED. Maybe we'll learn during the next talk. So but so far we just focusing on all the display processing where you do some kind of pitch conversion, which we see from, let's say, from watch display size. Below this, like AR, VR, more AR, we don't see any need to do a single transfer or other jobs.
Okay. So thank you again, Oliver, for your presentation and participation. Thanks a lot. And now we can move to our next speaker, Soren Studel. Soren, you are a co-founder and CTO at MicroLED, Micro Display. So Soren, you can share your screen. The floor is yours.
Okay, thank you very much, Jeremy. I would like to just go in the opposite direction from the previous speaker, Oliver, because actually I really would like to speak about how to make micro displays for AR. And I'm actually now clicking on share, and okay, no. It's rather slow until it comes. Can you see actually my screen?
Yes, you can start. Thank you.
Okay, thank you very much. So manufacturing challenges, Oliver talked about manufacturing challenges of micro LED for flat panel. The complete opposite in terms of infrastructure and specs is micro LED for AR. I always like to start with a very technical slide, just saying, what do we actually need for AR? And for AR, okay, Uwe Vogel already said, hey, these are the different optics concepts. But if you want to go for AR, then I would say the main concept is still the waveguide concept. And for waveguide, you need a display which is a very high resolution. We talk below 3 micrometer pitch. Otherwise, you don't have a small enough chip. You need crazy brightness levels. 1 to 10 million nits white light. Power consumption for the user scenario should be actually okay as well, much below what. Image quality perfect. So laser scanning is, for example, always a problem with this approach. And then, of course, most important, you need to be able to manufacture it for a reasonable price, similar like a mobile phone system. And all those specs together, you need to achieve for AR. And actually, no existing this big technology can do that. And that's why everything hope is on micro LED. But micro LED for AR, I said already, you need to have 3 micrometer or below. Otherwise, you need at least full HD or larger. The chip is too big and there's zero yield. So 3 micrometer, what options do you have? You can, of course, start with a die-to-wafer transfer. You make a 3.5 wafer in a 4-inch, 6-inch fab. You take the 300 millimeter wafer from the CMOS, and then you do indium bumping. Now, this is done standardly for infrared imager, and it's an established process, but established is as well a good yield. You only get up to 8 micrometer, maybe 7 micrometer. And if you want to go far for space, military, you can show a nice demo for 3-4 micrometer, but it's actually not a credible way to go. Because it has been done for infrared imagers for 20 years. Why would the micro LED be something very different? So the problem is really actually how to make the integration of the 3.5 with the CMOS. And the only credible integration approach below 8 micrometer is you go to a full wafer monolithic approach. And that means that you basically go either sequential 3D, you have put a metal layer on a 3.5 epi wafer, you put a metal layer on a CMOS wafer, bond them together, and then you make basically pixel isolation. That's, for example, like JBD in China is doing it, credible concept. Or, and that's what we think is the way to go, is you go to the standard established wafer-to-wafer hybrid bonding, where you take 2 equal-sized wafers and bond them together with hybrid bonding, dielectric, metal. And that's how you actually produce an imager. Now, we think that's the only credible way to go if you want to have high volume in with the right precision and with the right yield. The problem is, of course, first thing is the CMOS is a 300 millimeter wafer. The epi is normally not a 300 millimeter wafer. And you basically need to solve those integration challenges. And that's what we're up to. And then the second challenge, which I always like to talk about, is how to make color. And there are endless concepts of how to make color, but all of them have actually some drawbacks. And I would just like to shortly point out what are some of those drawbacks, because it's always important to know what are the limitations. The drawback, for example, you could make an individual die to laser transfer, similar like Coherent showed about micro LED on flat panel. But now, if you talk about a pixel pitch of 3 micrometer, minimum 6 million LEDs per die, 0 defects pixels are normally in the consumer mobile phone and consumer space required. There's no credible yield possible. You can go to color down conversion. You transfer an epi die onto the CMOS readout and have blue LEDs, and then you make down conversion. But down conversion normally, if you target 1 to 10 million nits, you talk about 5-10 watt per square centimeter blue light. No quantum dot perovskite nanophosphor material can get that right now with a good lifetime. You're an order of magnitude off. Nice concept recently shown is dynamic pixel tuning. You basically, different current densities have different wavelengths. But of course, that means for red, you apply maybe 1 amp per square centimeter, for blue, 100 amp per square centimeter. And then you need to balance RGB. And actually, you're limited by the one which is red, which is the lowest brightness. So in the reality, you will not get much above 20-30,000 nits either. So what is left is basically what we take as our first approach, and the same approach is, for example, shown by JBD as well. You use an optical combiner, make 3 separate dies RGB, and then you can do that with a waveguide or a prism combiner together. And then, of course, there's still a lot of other concepts, how to stack the AP layer together, stacking them by growth, by bonding, or stacking the complete LEDs. All of them will have impact on the efficiency. Basically, yield will be a much bigger challenge, and efficiency will be a much bigger challenge as, for example, if you just go for the optical combiner technique. And last, to talk about technical specs at the beginning, it's performance. And Uwe Vogel already said, hey, a micro LED is unlikely to be more efficient as an OLED. I fully agree with him, because your losses are actually based on optics and not necessarily based on some recombination losses. And optics simply dictates, okay, you want to have 10,000 PPI, that means below 3 micrometer pitch. You know what your internal IQE from the different AP wafers, gallium nitride, AlInGaP is, and then you know what's the N value of those materials, how the light goes from the materials itself into air. And then you know how much light can couple directly out. And if you want to get more light out, as those here 5 to 9%, then you basically need to actually catch wave-guided light and get it out. Now, if you have a large LED display, let's say an LED 5 micrometer with a pitch 10, 15 micrometer, that's not a problem. You can maybe put sidewall mirrors in, catch wave-guided light, and have given another chance to get the light out. But if you have actually a 1 micrometer AP layer, you have it in a 2-3 micrometer pitch, there's no way that you can get wave-guided light out. And then you still, of course, need to be able to focus light. And there, of course, there's some advantage what you can do with micro LEDs. For micro OLED, you always have a Lambertian emitter, and it's not so easy to make on an OLED a focusing structure. On an LED, you can make a focusing structure, and that's really the benefit. And that's basically all of those three things come about what I want to talk about manufacturing. Why is it important for yield? Now, actually, the reason why we as Migledi, we are a startup 5 years old, and we were founded because we perceived it as a problem to get, how do you make manufacturability in volume? And manufacturing in volume, that means, hey, you can start with an R&D process, make a beautiful demo, and then you can build basically a fab around your beautiful R&D process. But you will spend 100, 200, 300, $500 million, depending on, do we talk about the 4-inch or a 300 millimeter fab, just to build the most simple fab. And you will immediately have a capacity of 50 to 100 million units. And if you want to fill this fab, if you don't fill it to at least 80, 90%, you will lose money. Now, you know that AR market is not yet there. So we say, okay, the only way how you can do it is you simply assume that you can make a process which can run in a standard CMOS foundry, use existing tools, but then of course you need to make the full process flow that it can really work into a standard existing foundry. And that's the concept which Migledi pursues since we spun off from EMEC. And we use really production tools at the pilot line of EMEC to make our developments. And the developments is really about the concept of what can you do with yield. Yield is everything. And basically, Coherent talked about transfer yield. In our case, we talk about really pixel yield. Consumer product, you need zero pixel defect density. So you need to use processes which you know from semiconductor that you can get perfect yield. And perfect yield is, for example, the 3D backside illuminated imager, where you stack basically a diode array on a CMOS wafer with something like 100, 200 nanometer overlay down to 1.5 micrometer pitch in production and 500 nanometer pitch in R&D. So now we need, of course, to replace the 300 millimeter silicon diode wafer with a gallium nitride wafer, which we actually don't have. So how do we create it? We basically take in best-in-class AP wafer, 6-inch, 8-inch, redistribute AP dies on across a silicon wafer, which means every AP die is basically the size of the final display, full HD, for example, 4x6 millimeter. We redistribute the AP, remove it so that there's no only 1 micrometer of AP left, and then we planarize it. And basically, we have now a stress-free silicon wafer with a super thin AP layer, and we can move it through a standard CMOS fab. Use the same process like we make a backside illuminated imager. And that you can actually see here. You can see here how actually a single LED looks like. You see basically the back end metallization, copper metallization of the silicon wafer, bonded to the LED, and then you can see here the emission zone in a 1.52 micrometer large emitter. And you can see here, then you look on the 300 millimeter wafer, you zoom in, and then you can see really a die. And this array is basically the size already corresponding to full HD. But in the first approximation, we actually didn't use a CMOS. We used just a metal silicon wafer with some metal layers to really develop the process and then design the backplane. And with that, we can get a reasonable yield already now, even though we don't use only a pilot line. And the alignment accuracies between the front and back end wafers is easily below 200 nanometer. So, and we can basically process as well wafer level optics on top of that with super high precision. Just an example how it actually looks, if you look at the die, this area here is basically the gallium nitride, and here we have then test patterns, either in blue, green, red, which you can see. And you can, this is, for example, as 1 square millimeter big face of John Lennon, 480 by 320. And you can basically expand it. And even if you expand it by factor 3000, you still have enough light in daylight. So that means you are in a few million nits. And you can put it in glasses. It is now, of course, not video capable yet, but if you take it in a standard commercial waveguide, you actually can see that it's really bright, that you really can work in bright daylight against the sunlight. Now, one thing which I always want to mention if I talk about efficiencies, Jürgen mentioned micro LEDs are not much more than efficient than micro OLEDs, only they can sustain much higher current densities. And I said already, the real efficiency within the apex angle, which is relevant for us, is normally in the range of 1–2% more is theoretically from the optics not possible. But still, people sometimes measure up to 8, 9, 10% at 3 micrometer pixel pitch. How is that actually possible? And the explanation is actually quite simple. If you have an emitter, which is really emitting, you get maybe less than 9% of your light can you directly get out of your pixel. But a lot of the light is wave-guided. And this wave-guided light is then scattered at neighboring pixels. And if you just use, for example, an integrating sphere, photodetector, etc., you will always measure this light. And then you basically will completely overestimate your efficiencies. Now, as an example here, I take a paper by one of our competitors, and that's already one of the best ones. They make a lot of effort to eliminate the wave-guided light. But already from the published curves, you can see that you have something like 3–4% of the light is still in the neighboring pixel coming out. If you integrate it over the full 2D area, you measure immediately that you are here overestimate your light by maybe factor 1.8. So I want to repeat, efficiency is better as, let's say, OLED, you will likely not achieve, but you can achieve much better brightness because you simply can pump in 2–3 orders of magnitude higher current density in. And of course, one question is always, how can you focus more light? The good thing is you're talking about a solid semiconductor system. You can basically process things like Fresnel lenses on top of that with super high precision. Here we make multi-level Fresnel lenses with 20 nanometer alignment accuracy because we use the latest generation of immersion steppers. And then you can basically focus shallow beams, bend them upward, and get more light out. And in addition, you can get a great crosstalk. So where we are now, we basically used our seed funding to prove that we can run this process flow on production tools, and we can really show blue, green, red gun. In parallel, actually, we were working as well as on ALA-INGAP, but there the challenges are more about how to make that CMOS fab compatible. We have now started the process actually to transfer this process to a foundry. But most important, we basically now are in the process of actually making our ASIC design. Advanced node ASIC design takes a while, it's very expensive, but we hope to be out with our product in Q4 of 2025. And that's kind of like a mix out of a scientific story as well as about technology challenges about making the micro LED for AR. And I only want to repeat, the biggest challenge is how to make production ready. And we think the only way how you get the price and the quality point is if you do it on a 300 millimeter processing line, actually in a foundry. And if you look at cost of your display, and I'd say the bill of material should be below, like a mobile phone display. Your AP defectivity determines your final die yield. That means, for example, sapphire, if you grow GaN on sapphire, it has a very high defectivity normally compared to GaN on silicon. This is already a big problem. And finally, about efficiency, actually, the efficiency is limited by optics, so you lose basically all light below the angle of internal reflection. And that's basically what we are contributing to the photonics development in Europe.
Thank you, Søren. Thank you very much for your presentation. Any question for Søren? You can raise your hand through Zoom. I was wondering, Søren, that you are mainly active in or you are mainly targeting AR market, but yeah, you mentioned it, but we don't have any AR market for now yet. I hope for. But do you plan to expand beyond AR market into other kind of industries like wearables or maybe medical devices? Is this something that you also investigate?
No, we have the specs which we have. I said at the beginning, what are our specs? And the specs which we target are rather crazy specs. For every, if I can drop any of those specs, I have competition with LCOS, with micro OLED. For example, micro OLED, if I drop the brightness, micro OLED is an excellent choice. And it's already a relatively mature technology. So you run basically against existing markets and you try to compete basically on price. This is for let's say a startup company, a hopeless proposition. The only thing is if you have applications where you really need those crazy specs, the density, the yield, and that means this for us AR. Secondary as well, we get a lot of interest recently for automotive because you talk about pico projector HUD displays where you basically, if you can use a single chip to project, let's say a 10 by 10 centimeter area, and you get the chip price small enough to get, let's say, get overlapping areas. That's actually a value proposition. But for that, you target again, you need to be somewhere in the not only 1 million nits, you need to be rather in the 10 million nits.
Yeah. Right. Thank you, Søren. Okay, so if we have no other question, thank you very much again, Søren, for a nice presentation. And yeah, I already mentioned it, but we have this event on AR at More Photonics next year. So just stay updated about this event. It will be in June 2025. I think you could be interested. So thank you again, Søren. And now let's move with last but not least speaker of the day. So Peter Karp. Peter, you are sales and support manager at Mezi.
Correct, yeah.
So please, Peter, you can share your screen and start your presentation. Thank you.
Thank you very much. Just a second. Do you see everything?
Not yet. Yes, please.
Okay, great. So now we've heard a lot about new display technologies, and I want to recap a little bit, but also then talk about the measurement challenges you have with some of those technologies. So here's a quick overview of developments of the last years. So we still use, to a large extent, TFT LCDs. OLED, AMOLED displays are very common now in our smartphones. And since 2013, we had the first introduction of QLED, that means with quantum dot technology. MicroLED was introduced in 2012 already, but the first real product 2019, and that is something which is now, like we heard today, really strongly evolving and for different areas. We have since 2022 quantum OLED and are now looking into so-called true QD LEDs, that means self-emissive displays in that case. And those new display technologies provide some advantages, especially that they have a very high dynamic range, very low luminance values, very high luminance on the other side they can achieve. And that can be a problem, or at least something you have to take care of when you need to measure that. And when we are talking about low luminance values, we are talking typically about 0.01 candela per square meter, or typical real world very low values are 0.005 candela per square meter, can be even lower than that, because OLED, for example, by definition, does not show any light when you switch off the display, so you have infinite contrast in theory. Of course, then in the real world application, you have some reflection on the display, but from the low luminance value, you can go very, very low. On the other side, the new technologies, like we just heard as well, can go up very, very high. So it's now very common that you have displays with 3,000 candela per square meter or 5,000 candela per square meter for outside applications, or when you have small displays and you have to realize really high luminance values as well. You have displays with 20,000 nits and above, even for backlight units, really high values up to 100,000, which you need to measure very accurately as well. Then the new displays have one advantage compared to our old CRT-based Rec 709 color gamut. They achieve a very wide color gamut, which is now, for example, defined in Rec 2020. And to realize this large color gamut, you need to have a display where you have the typically 3, but can be any other number as well, not any, but 3 or more primary values. They need to have a very narrow spectral power distribution. And then you can achieve a really so-called wide gamut display with very, very saturated colors. But that can be challenging to measure as well. For AR/VR applications, but also for applications like, for example, a smartphone, you have very small displays you need to measure now. In some cases, you want to evaluate on a pixel level. And finally, you also need to take care that you assess the viewing angle characteristics of your devices. Most of the modern display technologies have a pretty good and very not so strong dependence on the viewing angle. But to achieve that, especially in the development phase, it's important also to characterize the viewing angles. And some technologies still have some problems with that as well. And what do we measure? So first is the brightness. Brightness is not the correct description of that. The correct name is the luminance, which we measure in candela per square meter. But the luminance directly correlates to the brightness we perceive as a human. The next value we typically will measure is the so-called chromaticity, mostly expressed as small xy values, but you can also transfer that to other color coordinates. They are calculated from the pre-stimulus values x, y, z, and then describe a specific color. And you measure, for example, red, green, blue, white, and black, several gray steps typically. But for some applications, you might measure, for example, even up to 5,000 color patches, for example, to calibrate a display, a TV. That is an application where they use a really large set of colors. And that means you also need to be able to measure very fast to make all those measurements in a reasonable time. And then finally, in some applications, you want to assess the spectral power distribution as such. So here is an example of a SPD from a quantum dot enhanced film. And you see that it's also relatively narrow, but can be even narrower than that. That is a relatively old picture. And there are two possibilities how you can measure all those values. So the luminance by stimulus values or the spectrum. You can either measure a single spot on a display. So that can be a very small spot, 1 or 2 millimeters only. Or it can be a larger spot. Typically for not too small displays, you will measure a spot size of a few centimeters. So you want to assure that you have at least 500 pixels at the same time in this measurement spot, so that you are not dependent on slight variations in the placement of the probe. And then the second possibility is that you want to assess the color characteristics and everything spatially resolved with a so-called 2D imaging colorimeter. And Admesi offers for both of those measurement types, spot and 2D imaging measurements, different solutions, our Prometheus series for spot measurements and the Titan and Helios series for 2D imaging. So when we have a look at the luminance range we want to measure, the first thing we need to take care of is the low sensitivity, or sorry, the low luminance range. And to measure very accurate, you want to have a very high sensitivity. So with our colorimeters, we can measure down to, and now you have to count, 0.0000025 candela per square meter. So extremely low luminance values in just a second, or more typical would be 0.005 candela per square meter in half a second with a really good signal to noise ratio. You also need to make sure that you have a good handling of the noise characteristics, so dark current calculation. For some devices, you use a cool sensor, and for our spectroradiometers, for example, we achieve a super large dynamic range of 0.005 candela per square meter up to 10 million, and have an excellent signal to noise ratio of 1300 to 1. The device uses neutral density filters, which also helps to achieve that large luminance range. And for the colorimeters, we have a ultra high luminance sampling mode, which extends the luminance range even further, also for the colorimeters as well. To measure the narrow spectral peaks, you need to differentiate between the colorimeter or spectroradiometer type of instruments. So when you're looking at the colorimeter type, then you want to have a small F1 error. That means those curves you see here, those are the so-called color matching functions, and they describe the vision of our human eye, so the sensitivity of our eye. It's not the sensitivity of our cones, but it's correlated to that and basically comes down to the sensitivity of the eye, how we perceive the colors. And so you need to make sure that the filters you use in those instruments are very accurate and that they match to those target functions as good as possible. And a small F1 error of, for example, about 2%, which is exceptionally good. That means to compare the area you have under each curve from the target to what you achieve has a mismatch of, for example, 2% is exceptionally good. And then you have a very low uncertainty of the color value you will measure. And the same is true when you look at imaging colorimeters. In an imaging colorimeter, you have the additional need that you also need to make sure that the filters are not only accurate as such, but also over a very relatively large area. That is a bit harder to achieve even. For the spectroradiometers, you need to make sure that you measure with a high resolution so that you can resolve all those small spectral bandwidth peaks. We offer instruments with an FHWM, full width half maximum resolution of 2.8 nanometers or smaller, but that can be customized with different slit sizes or gratings of the instrument to really match the target of a customer. And the wavelength accuracy of such a high-end spectroradiometer is really, as good as it gets, what you can physically achieve with a wavelength accuracy of only 0.06 nanometers, so extremely accurate. You can describe those small peaks. And for small displays, you of course need to make sure that you have small probes, so with a small measurement spot, and that goes down typically for our instruments to 2 millimeter. And for the spectroradiometer, you have even the possibility with a small measurement angle you can choose in the instrument and a macro lens to go down to 1/3 of a millimeter as a single measurement spot. And finally, we will have a look at the viewing angle characteristics. So for that, it is important again, for a colorimeter, for example, you can realize that with different acceptance angles, that means the angle under which the instrument collects the light from the display, and you want typically to have an acceptance angle of 5 degrees or less, because then you will not take into account the light rays which come from a very steep angle on the display. Because if you would measure with a wider acceptance angle, you gain sensitivity. That is the advantage. But the disadvantage is that you average or you smear out the measurement and do not really describe the display from the perpendicular viewing direction, but also take into account light rays which come from an angle which are typically you don't want to measure in that case to make a spot measurement. And this is a difference we compared to our competitors, that sometimes they use a larger acceptance angle to get a higher sensitivity. But with our patent pending electronics design, we can achieve a super sensitive device and can then use a relatively small acceptance angle to have very accurate color measurements. And then for some instruments, it's also important that you have a low sensitivity to polarization, so that you don't get errors depending on the polarization direction of the light. And in the end, when you want to assess the viewing angle, so exactly describe under which angle a specific color is seen, then you can do that with a so-called cornerscope, which measures a single spot. But this single spot collects the light from all the different angles, for example, plus minus 50 degrees, and then tells you in a resolution of, for example, 5 degrees, the different colors you will see under different angles. And that is a measurement which can be done with one measurement shot, so to say. So as Admesi, we offer time-proven, tested display testing solutions. So we are now in the market since 2006. And the solutions are very accurate, easy to integrate in production environments, and very robust. But we also develop custom products, and actually many of our standard products started as a custom product that a customer said, I have a specific need, and can you develop something for that? So we have very innovative designs, some patents pending, especially our experience in high-end filter coatings is now very interesting. And this is something where we are always looking to find partners, not for the filter coating, but in general, in all areas when you think it could be interesting to work with us together as a potential partner, or if you have ideas for a product, if you have measurement needs which are not covered yet good enough with the current equipment, just reach out to us, and then we can see what we can develop together.
Perfect. Thank you very much, Peter, for your nice presentation. Do you have any plans to implement AI or other kind of advanced image processing into your measurement systems?
Currently, we don't have AI approach in the measurement solution. So we are basically a hardware manufacturer, and we also provide some algorithms which we implement, and they can be implemented in firmware so that they are very easy to use, but also very fast, because the calculation is done inside the instrument. But currently there's no, at least then I know I would need to talk to R&D if there is a current plan to incorporate AI methods or not, but I'm not aware of that. And some of our customers develop their own measurement or evaluation algorithms. So they use the instrument and then integrate that in their own software. And sometimes we even do not know or are not allowed to know exactly what they evaluate, because the large customers, they have proprietary algorithms they do not share. So
okay. Makes sense.
We have to deal with algorithms only to a certain extent.
Sure. Any question for Peter? Okay, so thank you again, Peter, and so thank you to all the participants who are arriving at the end of the meeting. So we hope that you enjoyed it. So we'll have in January, and invite you to check the EPIC website. We'll have a market report presentation, online market report presentation related to display technology. So I invite you to check this, of course, if you are interested. And yeah, I would like again to thank all of our speakers of the day. Thank you very much for your participation, for making this event a nice event, and also all the attendees of today's event. So thanks a lot. And if you need to be in contact with one of the speakers today, feel free to send me an email. Thank you very much, and see you next time for another EPIC event. Thanks.
Nice evening.
Thank you.
Thank you very much.
Thank you. Bye-bye. And